Okay, the next important topic is about instant segmentation. So we discussed about the semantic segmentation now. Now let's go to the instant segmentation. So the idea is pretty simple. So instance segmentation is like you need to identify each instance of the object in the image. So basically you classify the pixels and you not only classify that, okay, this is a cow, but this is the second cow as well. Okay, so the pixels are not belonging to the same cow, so that kind of distinction is also needed in the case of an instance segmentation case. And that's why it's different from semantic segmentation, because in semantic segmentation you don't need to color them different, it will be like single color for the entire cow. Okay, and how to approach this? So one practical way is we can leverage the object detection approach. So you take the image, you detect the objects in the image, and then you kind of identify, okay, there are two cows in there, you kind of color the pixels into two, right? So that's the idea. So you do the object detection task first, and on top of object detection you can do some more post processing or some more loss function to come up with this. So having said that, the easiest way is actually to leverage the faster RCNN and then add a segmentation layer to the top, and that kind of uh, gives you this power of instance segmentation. So let me quickly recap the architecture here. So you have the input and the out, then it will be processed through a classical um, ResNet encoder or any encoder of your choice. So you have the feature map. So this will be some convolutional feature maps which is here, and that feature maps will be used to propose the regions, right? So the bounding boxes. So uh, please go back and see the video on faster RCNN for a revision on this, but a quick recap is, so feature maps will be used to predict the bounding boxes on each of those layers or each of those channels, right? And then of course you do a this needs to be trained, and that is we already discussed about it. You will have a classifier head which will only tell whether an object is present there or not. It doesn't classify them into different objects, but just say presence and absence of an object. So it's a binary classifier here. And then the other one is the bounding box regression, which will kind of predict the xy coordinates of the bounding boxes, which will be the prediction. Okay, so you assume that this is trained and you have the proposals here, and that proposals will be on each of these convolutional layers which are on not same resolution as your original image, right? So image, let's say it is h cross w, and here you may have the feature maps at h by n cross w by n, some fraction, right? So it's not the same resolution as your original image. So you need to map these proposals, these bounding boxes onto the feature maps, and then you need to check with the ground truth annotations. So how do you do that? This process is known as ROI pooling in fast RCNN. So it's like your original bounding box will be reduced or up downsampled and put on the feature map of that size, whatever size, right? So that process was known as ROI pooling. We explained that during the discussion of the faster RCNN case, but the issue there when we use it for the segmentation is like there may be a small change or small resolution issue, because you cannot have one-to-one relation between h cross w and h by n cross w by n. Some points may be here and they're off, right? Some points, let's say higher image to a lower, so it may be kind of not exactly matching. So this is not matching to any of those locations here, which would have been. So one way to kind of overcome this problem is you do an interpolation. So this is the point that I observed, but I need to map it to one of these points outside, right? So one is like nearest neighborhood is what we use, and that is ROI pooling. So you, this is closer to this, so I'll map it to this point. The other way is kind of do an interpolation just like the bilinear interpolation, and then predict the corresponding value. So you have this size, you want to reduce to this size, so what will be the corresponding value based on interpolation technique, and that's what we call as ROI-Align, and that's what they used actually in the MAsk-RCNN architecture. So it's ROI pooling, which was used in the faster RCNN plus interpolation. So if it is not closer, obviously it will not be closer, because you're going from a very high resolution to a very low resolution. There cannot be a one-to-one mapping. then you can just do ROI polling and then nearest neighborhood, that's it. The other way is to do an interpolation, which is typically known as ROI-Align. So this was introduced in this particular architecture in that sense. And this is important because you need to ultimately map it back to a mask which is of the same dimension as H cross W, because these layers which is originally there, after this you pass it through the softmax for category classification and the bounding box. So this is the object detection, but we are adding a head for the segmentation here, and that's why it's called MAsk-RCNN. And for that you need to come back to the same resolution as the original image, right? So you have these and then you do the upsampling here, and then you have the same dimension as, so this dimension and this dimension has to be same, right? So for that, this ROI aligning is important, because if there is a small error in this ROI pooling operation, that will kind of back propagate, or it kind of increase the error when we project it back to the original image size. Okay, so that's why they introduced this concept of ROI align, which is in a simple way, it is nothing but ROI pooling, just reiterating it, plus interpolation. Okay, so that's the advantage of doing this. Okay, and in MAsk-RCNNs, obviously there are 3 losses, or in fact if I include these 2 for region proposal, let's ignore it for the moment. I have 3 losses. So one is for the classes, so each each bounding box will have a class, will have a coordinate, and correspondingly a mask. So that's exactly what we want, right? So that's easy, you just added a head, that's all. The remaining everything is same, and then they found a problem with ROI pooling, so they introduced ROI-Align. Okay, so I would put this way: faster RCNN plus ROI-Align. Okay, so that will replace ROI pooling plus a additional mask, or this is the encoder or decoder part, in fact, is what makes it MAsk-RCNN. Okay, so this is the idea. Okay, and then of course loss functions are one for bounding box, one for category, and the third for the segmentation. And of course I think we never discussed what is the loss for the segmentation. So segmentation loss will be the mask or the segment minus your ground truth, and you can do it for the L2 sense. Okay, so you do the mean square error between these two for all pixels in that sense. And the ground truth of course is done by uh, us. We need to annotate. You take an image, so let's say this is an image, I'll just mask, let's say this region, so this will be a ground truth mask that will be coming here. This is human annotation. Okay, I think we didn't discuss, apologies for this, during the semantic segmentation class, but this is what exactly it all about. I hope it's clear. So you replace ROI pool with ROI align, and then yeah, of course they also introduced, in addition to this masking part, they also introduced a feature pyramid network, which is like a structured uh, encoder kind of architecture for the MAsk-RCNN, but it's not really, because the feature pyramid network is very common nowadays, so you don't need to worry about it or need to understand that as a separate entity, because that's what typically we do. Okay, I think, yeah, so these are some interesting results we can see from the paper. So they are able to kind of do, you can see the instance segmentation very clearly. All of them are persons and they are separately identified in that sense. So the idea is, key idea is object detection followed by uh, segmentation, right? So you need to, so classification plus object detection, typical, you add a segmentation on top of each of those objects detected, you add segmentation. Last but not the least, I'm not going to deep dive into this, is panoptic segmentation. It is a idea where you kind of divide everything in the image into its classes. Okay, so you can see that here. So everything in the image is kind of divided here. Label all the pixels, and this can be done in a variety of ways. So this is for self-study, but you can see you studied about instance segmentation, you studied about semantic, and you know how to create the backbone, which is nothing but an encoder. You can kind of combine them in various ways and come up with the panoptic segmentation architecture. So please have a deep dive into this if interested. So I'm not going to discuss this in a lot of detail, but this one is discussed, this one is discussed, this one is discussed. Obviously we'll be able to understand this without any issue. Okay, and now coming back, or coming fast forward to 2024, the state of the art is a model from Meta, which is known as segment anything model. And the idea is it is vision transformer based. So we will discuss about the backbone of this when we talk about vision transformer, which is the next lecture, obviously. And the interesting part is it can take various kinds. So the concept is same. You take the image, you encode it, you have the image encoding. So this is a typical thing, and then you can decode it, right? So that's a typical kind of architecture. There's no difference. But the major thing they added is you can actually do a lot of prompting. You can actually do a bounding box or mask or text or point. So let's say I click on this point, it can segment. Okay, so you can segment the entire scissors out. So that is the uh, important aspect. So it's a the prompting or there is a user interface to the segmentation task now, and that is basically the way they have designed it. But the architecture is encoder decoder, but using vision transformer. the the key interesting idea is basically the prompts that the user can give a mask. User can click or point to a particular region where they want to put the segmentation, or can draw a box where they want to, or even use a text prompt as well. So that is the idea. So let's do a quick demo of the segment anything model, and that will kind of so I'll just show you here. Of course, I'll add this, and let me click on any image here. So it will create an embedding, and then of course you can use any of these tasks here. So let's start with maybe a box. So I'll draw a box around this, and that's segmented already. That's nice. So let's try out this everything, which means it will divide the image into equal number of grids, and then kind of identify the key points, maybe using region proposals, and then do the instant segmentation on that. So it's interesting actually, but all these are done using vision transformer backbone and decoder. Okay, so that's the idea, and please have a tryout on this, and let me go back to the slides. So that's all on the segmentation side. So just to summarize, segmentation is like parceling or segmenting the image based on similarity, and there are various ways or types of segmentation. Semantic is like I don't care about similar objects, they will all be grouped into one, and it only care about dissimilar objects in that sense. Instance is like every instance of the object you need to segment, and panoptic is like you segment really everything in the image. And then of course we discussed about the latest, the state of the art model, which is segment anything model from Meta. Key concepts learned in this few lectures on segmentation: one is unpooling, okay, a new way to kind of upsample the feature maps. Transpose convolution is the kind of standard way of upsampling or increasing the size or resolution of the feature maps. At-rest convolution is a novel way to kind of introduce wider receptive field. In that sense, it uses dilation plus group convolution. And then of course skip residual connections, where you really don't add up the residual connection, but rather concatenate the residual connection in unit. And then of course RoI-Align in the case of MAsk-RCNN, which is nothing but ROI pooling plus interpolation.